In this video, we're going to be looking at a subset of alkene molecules and looking at the question of what happens if we take a ring structure and we put a double bond in one of the bonds in that ring structure. Well, the first and most obvious answer is that we end up with a type of hydrocarbon that we call a cycloalkene. So cyclo obviously tells us that the structure is in ring form, while the ene suffix indicates that there is at least one carbon-to-carbon double bond that we see right here. Now, the first difference we can observe by comparing a ring structure with a double bond with a straight chain, or what we can call an open chain alkene molecule. We call it an open chain in that each of the carbons in the parent chain is relatively free to move around, as opposed to the carbons within a ring structure that have restricted freedom of movement because they're all held together in a ring. Now, if we consider but1-ene that we see here, let's actually make a quick modification and let's get rid of these two hydrogens here and replace them with bromine halogen substitutions, or bromos, if you will. So here we can see that this but1-ene derivative here is clearly in the Z form because each of the bromines falls on the same side of the of the double bond in this case, but we can see because this is an open chain, because carbon 4 is not attached to carbon 1 in a ring structure, if we wanted to modify this and get the E form, we could do that relatively easily just by breaking the bromine off of this location here and replacing this hydrogen with the bromine here, and then now relatively easily we have the E form because the two bromine substitutions are now on opposite sides of the ring. So here in an open chain alkene, both the E and the Z isomers exist relatively commonly because there is no ring, rather, to restrict movement of each of the atoms. But we can see that in ring structures, this is much harder to do. So if we were to substitute each of these hydrogens in the ring structure with bromines, well, now it's very obvious that we can have both of these bromines in the Z configuration here. But because the downside of the ring structure is actually part of the ring structure itself. So this carbon is attached to this carbon here, and this carbon is attached to this carbon here, and somehow, if we wanted the E form, we would need to substitute this bromine for this carbon in the ring, but then the ring would not be physically possible. And so we see that ring structures, even though there is an alkene present, are basically stuck in the Z configuration because of the fact that the downside of the double bond is actually part of the ring itself, and without breaking the ring entirely, it would basically be impossible to take this bromine and swap it with this carbon here without destroying the ring and making the molecule unstable. And therefore, because ring structures with a double bond are basically locked in the Z configuration semi-permanently, most of the time we do not consider EZ isomers at all in cyclic alkenes that we see here. Now, as a consequence, the naming system for cycloalkenes is significantly more straightforward because we don't really need to bother with E or Z forms, because modifying one to the other would destabilize the ring. So the rules remain relatively simple. Look for the parent chain, which in this case is 8 carbons long, so this would be a cycloalkene. And again, note the consecutive vowels that we have here, flaunting English's ignorance of its own rules here. Now, the shortcut that we can use to simplify things, we haven't talked about precedence and ranking the importance of components of an organic molecule yet, but because the double bond is part of the parent chain and not a side chain, the double bond is regarded as the most important structure, whether it be be part of a chain molecule or a ring structure like this, and therefore the number for this double bond is always going to be kept as low as possible. And therefore, if we designate this carbon here as carbon 1 and this carbon here as carbon 2, this puts our double bond in position 1. So our parent chain in this case would be called cycloalkene. And then all of our side chains would be named accordingly. So this would be 3, 4, 5, 6, 7, and 8. And on the surface, it looks like our side chains are not given the lowest possible number, and you would be right. But again, this is because the double bond takes priority over all of the other side chains here, which actually simplifies matters, because as long as we give the double bond position number 1, the rest of the side chains kind of play second fiddle to it like this. So we can see that chloro, or rather dichloro here, because we have 2 chlorines on 5 and 6, would come before our tetraethyl right here, because C is alphabetically before E. So we would have 5,6-dichloro followed by our tetraethyls, which fall on 3, 4, 7, and 8. And there is our tetraethyl. And then all that remains is to identify our parent chain, which is the cycloalkene molecule that we see, or that we have already named, like so. And if we want to do an example where we take the name and derive the structure, we see that this is a little bit more straightforward with one possible trick. We are building a ring structure here, in this case a 5-carbon ring. So let's go ahead and draw our pentagonal structure for the base of our molecule. And then we see here that we actually have 2 carbon-to-carbon double bonds, one in position 1, let's just call this carbon 1, and one in position 3, which would actually be between carbons 3 and 4 that we see here. And there is our cyclopenta-1,3-diene that we see here. And then from there, we can simply put our side chains on. So on carbon 2 and carbon 3, we've got bromines that we have here. And then on carbons 1 and 4, we have 2 carbon long side chains, 1 ethyl here and 1 ethyl here. And then finally on the last carbon, carbon 5, we have a 1 carbon long side chain for our methyl, and there we go. So again, the easy thing about drawing cyclic alkanes with double bonds in is because the ring structure basically traps the alkene within one of the E or Z forms, we can basically just ignore whether it is in the E or the Z position, because to get the other isomer would destabilize the ring, and so both of these are considered the default forms of the molecule. This concludes our brief series on cyclic alkenes. To test your knowledge of both the naming and drawing of cycloalkenes as well as alkynes, you can complete the rest of the practice examples below before the next series of videos introduces functional groups and the effects that they have on the behavior of organic molecules.